All right, number one, what is the conservation of momentum? So the conservation of momentum is this. The total momentum before a collision equals the total momentum after. So the momentum you have before will equal the momentum you have after. So if you have a momentum of 50 before a collision, you have a momentum of 50 after a collision. Okay, total momentum before a collision equals the total momentum after. The equation for this is P1 initial plus P2 initial equals P1 final plus P2 final. If there's three objects, it's just 1 plus 2 plus 3 initial equals 1 plus 2 plus 3 final. So frequently you'll see it, and on the practice that you get today, you'll see me with dots after the 2. You'll see it something like this. That's just to show you that it doesn't matter how many things there are. If there's 2, you add 2. If there's 3, you add 3. If there's 4, you add 4. It doesn't matter. We usually won't go more than 3. Also, I should mention, the before and the after can have different numbers of things. There can be 1 thing before and 3 things after. There can be 2 things before and 1 thing after. It just depends on the problem. All right, number 2, what is an inelastic collision? So an inelastic collision is where momentum is conserved but motion is not. Basically, there's some motion that's lost somewhere. So the momentum is conserved, but after the objects collide, they're not quite going as fast as they were before. They're going a little bit slower, possibly. It just depends on what the problem is. We'll talk more about this when we get to energy, because I can explain it better when we do energy. But momentum is conserved, but motion is not. A good example of this is a car wreck. There you go. See, in a car wreck, the objects change shape, and that uses up some of the motion. And so because it's using up some of the motion, where are you? There we go. Can't find it on here. No. I'll have to show it to you later. But objects, when they collide, change shape. If they change shape, they lose some of their motion, and they only conserve momentum. But every object will conserve momentum. It'll never be otherwise. All right, number 3, what does it mean if a collision is completely inelastic? So inelastic just means it conserves momentum but not motion. What does it mean if it's completely inelastic? It means the objects stick together. All right, so what are elastic collisions? So they conserve momentum and motion. All right, I want to show you one of each of these. I want to show you an inelastic collision, and I want to show you an elastic collision, what they would both look like here. Because it's easy to... This. All right, so bowling ball, the bowling ball's hit. It transfers all of its motion into the other one. It moves at the exact same way that the first one did. It changes a little bit if the masses aren't the same, but if the masses are the same, it moves exactly the same as the first one. All right, how does momentum relate to Newton's three laws? So we talked about Newton's laws. First law is inertia. So what does momentum have to do with inertia? Well, P equals mv. We said momentum is inertia in motion. So m is the inertia and v is the motion. So inertia in motion, P equals mv. M is the inertia, V is the motion. So that's how Newton's first law reacts here. The difference here is Newton's first law just explains why do things resist change. This momentum explains how it does that. So it actually explains how it resists change. It resists change because of its motion and its mass. So while a fast-moving object does not have more inertia, it is harder to change because it has more motion of its inertia. Okay? All right, good. Second law. Second law is F equals ma. All right, so I want to show you something. So here's the equation for, I'll kind of divide these off here a little bit. Here's the equation for impulse momentum. F delta t equals delta p. So let's go ahead and use the usual symbol for time of just t. And let's turn this into final momentum minus initial momentum. Well, let's simplify it even more. Let's do mass times final velocity, so P equals mv. So I just changed this P into mv minus mv. Notice the masses are the same because the mass doesn't change, but the velocities do. So there's a final and an initial. Let's go ahead and let's factor out the mass. So I'm going to factor out the mass. Ft equals m v final minus v initial. Another way to write this is mass times delta V. So delta is change in, final minus initial. So this is final minus initial V, so I wrote delta V. I'm going to divide T to both sides. Don't worry, I'm almost done. F equals M. What's delta V over T? Anyone remember? Delta V over T is? No, good guess. Acceleration. Oh my goodness. They're the same equation. I'm sure that blew all of your minds. I have good news, okay? Good news. On the test, I'm not going to make you do this, but you should know that they're the same equation. They are the exact same equation. They're just written differently. They're just written differently. This one is based off of momentum. This one is based off of acceleration. That's the difference. So one tells you how it changes. The other one tells you why it changes. This tells you why it changes. It changes because of the time interval of the collision and because of the momentum change. This explains how it changes. It changes by accelerating. There we go, last one, and then we're going to take a break. Third law. Every action has equal and opposite reaction. Let me just divide these up here again, just so we're not getting confused on anything. Okay? So, here's the equation. P1 initial plus P2 initial equals P1 final plus P2 final. Let's get the ones, don't worry, this one won't take as long. Let's get the finals, let's get the ones on the same side. So subtract P1 final to both sides. Let's get the 2's on the other side. Subtract P2 initial. That gives me P1 initial minus P1 final equals P2 final minus P2 initial. Final minus initial is delta P for object 2. Initial minus final is negative delta P for object 1. Every action has an equal and opposite reaction. Conservation of momentum is the third law. Again, I'm not going to make you do all these steps on a test, but you should be able to explain it to me. You should be able to explain to me that Newton's third law is conservation of momentum. Okay? You should be able to explain that conservation of momentum is that. Oh, stop it in time.